what we're going to see now is that we can actually solve this flow completely using the full Navier-Stokes equations, because a lot of things just drop out. So the first thing we're going to do is we're going to say, okay, we're studying the fully developed regime. So we're studying fully developed flow between two plates. So we've got two plates separated by some gap h. We've said that h is much smaller than w and much smaller than L. We saw in the last lecture that at some point the flow becomes fully developed. And so we're gonna say we're looking at the fully developed region now, and that means that du dx in particular is 0, because the flow is no longer changing in the x direction in either u or v, because it's staying the same velocity profile now as it moves down the channel. So we can use the continuity equation to come up with one conclusion very quickly. Du dx plus dv dy is equal to 0. That's the conservation of mass equation in 2 dimensions. All right, great. Well, we said du dx is equal to 0, so that's 0, which means that dv dy is equal to 0. Therefore, dv dy is equal to 0. Okay, well, that means v is not changing in the fully developed region in the y direction. But we know v is 0 at the walls, because the v at the walls is a no slip, no penetration condition. So we know that v is equal to 0 here, and it's also u is equal to 0 here. Everything, all the velocities are equal to 0 on the wall. And if the v isn't changing in the y direction, that means v is 0 at the wall. It's 0 everywhere. So v equals 0 everywhere in the fully developed region. All right, so that's going to give us eliminate some terms for us. Now let's take a look at the x momentum equation. So the x momentum equation in 2 dimensions, u du dx plus v du dy is equal to minus 1 over rho dp dx plus nu d squared u dx squared plus d squared u dy squared. So that's our x momentum equation, full form for steady flow. No unsteady terms there. Well, v is equal to 0, so that kills this term because that has a v in it. Du dx equals 0 because it's fully developed. So in fully developed flow, du dx is equal to 0. Also, this term, if you were to write it out, is d by dx of du dx. So this term is also 0. So we eliminate most of the terms right away. So we're going to rewrite this equation now with the only stuff that's left. The only stuff that's left are the pressure term and one of the viscosity terms. So the entire equation for this fully developed flow between two channels, between two plates, is plus nu d squared u dy squared is equal to 0. So that's it. Now we're going to move that so that one is equal to the other. So I'm going to say dp dx is equal to rho times nu times d squared u dy squared. Well, rho times nu is just mu. So I have dp dx is equal to mu d squared u dy squared. So that's my governing equation for this problem. It's a very simple looking equation. And in fact, it's easy to solve it because of another thing that we haven't yet observed. U, we know, is not a function of x. So u is not u of x anymore because we have said that u is not changing in x. U is constant in the x direction. That's what it means to say there are no derivatives of u and x, right? That u is remaining constant. So this right-hand side is a function of only of y. This term, well, we don't know about this term. Is pressure a function of y or pressure not a function of y? Well, in order to answer that question, we can look at the y momentum equation. So u dv dy plus v dv dx, sorry, u dv dx, that was a bad start. U dv dy is equal to minus 1 over rho dp dy plus nu d squared v dx squared plus d squared v dy squared. Sorry, I'll rewrite this because I screwed it up. dv dx plus v dv dy minus 1 over rho dp dy plus mu d squared v dx squared plus d squared v dy squared. There. All right, so that's the equation. V is 0, V is 0, V is 0, V is 0, V is 0. That means this equation is telling us dp dy is equal to 0. The pressure is not changing in y. So P is not a function of y. It's constant in the y direction. All right, so P is constant in the y direction. That means that P is only a function of x. So when we're looking at this equation that says dp dx equals mu d squared u dy squared, this term is only a function of y. I'll call it g of y. And this term is only a function of x. I'll call it f of x. And they're equal to each other. Well, if you have a function of x equal to a function of y, that means that they both have to equal a constant. There's no other way for them to stay equal to each other. No matter what this function is, if it has any x actually in it, and it can only have x as a variable, well, x could change, and then its value would change. And this function value wouldn't have changed because value doesn't have an x in it. And similarly, this function, no matter what it is, if it has any y actually in it, if it has a y in it, then y could change, and its value would change, and then it would no longer be equal to this function, who doesn't have a y in it. So y changing wouldn't change it. So the only way that those can be equal, they can only be equal if they both equal the same constant. So a constant is a function of x and is a function of y. It doesn't happen to have an x or a y in it, but those are both considered functions of x and y. So these functions can both equal a constant, and it's only by equaling a constant that they can actually be equal to each other.